Hello everyone, my name is Yair Zick, and today I'd like to share with you my work on providing good model explanations. So, as you may be aware, we now live in a world where AI decision makers operate in a variety of high-stakes domains, such as healthcare, criminal recidivism, personalized recommendations, and finance. And this setup where we have complicated decision makers make such decisions in high stakes domains often necessitates the use of model explanations. And let me just give you a short intuitive example. So suppose that I walk into a bank, well, somebody does, that's not my profile, and they ask for a loan from the bank. And the bank, unbeknownst to them, uses some kind of a decision-making model, automatic decision-making model to decide whether they do or do not receive a loan. And their loan gets rejected, and they ask the bank, well, why? Why was it rejected? And now the bank has a bit of a problem, because if it were a human that made that decision, they can go back and ask that financial officer, well, why was this person rejected the loan? That person could tell them, okay, well, this applicant did not have a high enough income or some other reason. But if they go and they look back at the automated decision maker, they might not be able to give them an obvious answer. So just looking at the model and its internal decision-making process could be very complicated, because nowadays AI relies on very complicated architectures such as deep neural networks, random forests, and similar techniques. So how do we take this complex system that sometimes even updates its own parameters based on previously observed data? How do we take how do we take that system and translate what it does to a language that an end user might understand? So to do so, we have an extensive literature that has really developed in recent years that provides model explanations. And there's a very large variety of such measures, but we're going to focus today on a very specific one, which is called feature highlighting. Or in other words, how much influence do different features have on a classifier's decision? And this class contains several very prominent types of model explanations, including Shapley-based, optimization-based methods, and gradient-based methods. And what happens here? Well, we take every one of the user's attributes and we look at what the black box classifier or decision maker does with them, and to a limited degree, and we output for every feature a value. So small values just correspond intuitively to features that were not very instrumental in making the decision, whereas high values, for example here expenses and income, correspond to features that were important in making the decision. Some features can have negative values. So for example, here the amount of check in the checking account is negative because even though it is important for the decision, it's actually important for the other class. So in other words, people who get loans, usually people with this amount of money in the checking account, actually do receive loans. So how does one design model explanations? Well, in my group, we try to look at a variety of design criteria. So for example, fairness. So is this model explanation framework treating different groups of individuals in a fair manner? Privacy. So is this model explanation leaking information about other users when it provides an explanation to a client? And finally, explanation quality. So how good is this explanation? Is it any good? Does it satisfy certain optimality criteria? And indeed, for quality, one can take two approaches. One of them is optimization based. So, well, you take the point of interest, which is the point you're trying to explain, you take a certain region around it, and then you try to optimize and locally find some local approximation, the best one you can in that small neighborhood. And then you use that approximation to explain the decision. Another option is to optimize in terms of how much the model changes its predictions when certain points are added or omitted. And finally, another type of optimization is gradient-based optimization, which is also a very commonplace technique. The axiomatic approach, which I will try to convince you today that it makes sense, essentially says this. Before we decide on a formula for our model explanation, let us try to decide what properties we want the explanation to satisfy. And then we will try to narrow down what mathematical formulas satisfy all of the properties that we have laid out. And I think this approach makes sense because the model explanation literature has blown up so much in recent years. So let's say that now you have this data set and you want to explain the decision of the model for this specific point. You go and you do a short web search and you realize that there are several techniques in the literature. So you can think about like gradient-based techniques, Shapley-based techniques, and optimization-based techniques. So which one of them should you pick? And this decision could be very important because the type of explanation you provide may or may not fit the use case that you have in mind. So how do you do it? Well, we advocate for a normative approach, or rather a normative debate about the type of explanations you would want to provide. So you start by saying, okay, I want properties 1, 2, and 3, and based on these properties, I would look at what measures satisfy them, and these are the measures we should be using. And there are two big reasons that I think this is important. First of all, because while the mathematical formulas can be very complicated, the properties themselves are fairly easy to understand. And more than that, it allows us to have a debate that not just includes computer scientists in order to decide what model explanations we should be using. Right? So we debate the norms that are easy to understand rather than the formulas, which are often at times less so. So let me briefly tell you about two such axiomatizations that we have come up with in my group. The first one is a Shapley value-based approach to generating model explanations, which we call quantitative input influence, or QII for short. Now, if you don't know what the Shapley value is, that's fine. It's basically a way of dividing revenue in a collaborative game theoretic setting, which nicely lends itself to the model explanation framework. And what this formula says actually is not very important. What does matter for the purpose of this talk is what properties it uniquely satisfies. And these properties are symmetry, so two features that have the same effect on the model will have the same value, dummy, so if a feature has no effect on the model, it has no value, monotonicity, which says that if a feature has more effect on the model, it should have more value, and efficiency, which just says that if, so the sum of the model explanations values should be some natural constant. We designed a slightly more data-driven model explanation, which we called monotone influence measures in a paper with Jakub Slavinsky, Martin Strobel, and myself in AAAI 2019. And this model explanations uniquely satisfies, again, a set of different properties. So geometric invariance, so basically the explanations move as the data moves. Continuity, so small changes to the data result in small changes to the explanation. Monotonicity, very similar to the monotonicity notion I described before, and non-bias. So if we randomly label the data set, with different values, the expected value of our explanation should be 0. So we are not a priori setting more value to certain features. We also designed, axiomatically designed model explanations beyond just feature highlighting, but to feature set highlighting. So saying how important was a set of features rather than just one. And the motivation is fairly simple. So if we look at this data point, which is a movie review, which is labeled as a positive movie review. If you read it, then indeed it's positive. It isn't the greatest sci-fi flick I've ever seen, but it is not a bad movie. Okay, so not glowing, but still positive. And you look at these two features, words are features here, not and bad. Then if you look at them individually, they both have a negative connotation. But if you put them together, then they have a positive one. So it does make sense to talk about the synergy of features and measure its importance rather than the importance of just individual features. And we have done that. So here is a way of measuring the value of a set of features. So here phi of S, so S being a set of features, so how much value do we place on a single, on a set of features. And here, this way of measuring influence satisfies a set of desirable axioms. Again, very similar to what we said before. So symmetry, invariance under merging. So if you take two features and merge them, then the total influence should add up as well. Monotonicity, again, similar to the ones we described before. And limit condition, very similar to the summing to a natural constant that we described before. But not only is this axiomatic, it's also optimal. So these phi or S, these set-wise values correspond to the coefficients of an optimal solution to a natural optimization problem. So let me just briefly go over a fairness issue that we do discuss in our work. You can go ahead and read it. So fairness, what do I mean by that? Just that, well, when we offer model explanations to different people, then we need to be aware that our explanation quality may vary between groups. And then how do we handle that? Right, so if we do we offer poorer explanations to different groups? Do we leak certain users' informations more than we do other users' information? So all of these things you do need to consider and evaluate as you study this interesting topic. And privacy is another important design paradigm, as I've discussed. And we already have shown in prior work by Reza Shokri, Martin Strobel, and myself that model explanations can indeed leak information about user data if you're not careful. And they do so especially badly for minority groups, again, tying back to the fairness concern that I've mentioned before. And we also try to take steps to mitigate this issue by offering differentially private, so provably non-data leaking explanations. And what we did here, we took an optimization-based approach. We tried to minimize some natural loss function in a differentially private manner. And what we did is we basically showed how to optimize in a differentially private manner using differentially private gradient descent, and how to handle repeated queries to the data, because every single query leaks a little bit of information. We want to make sure that those don't add up in a bad way. So before I stop, let me just tell you what the main insight I have from all of this is that when you design model explanations, you face an inherent trade-off between these three desirable design criteria. So if you want good explanations, you will have to trade off fairness to groups and privacy. If you want privacy, you may suffer in terms of fairness and quality. You want fairness, then you may suffer in terms of privacy and quality. So when you design them, you got to be aware of these trade-offs and work to mitigate them as much as you can. So that's it for me today. Thank you very much for listening. And if you have any questions, please feel free to reach out. Thank you.